At Smokeless Chimney, we have been working with the Angstrom Exponent. I want to give a historical breakdown, discovery, evolution, and the future of smoke measurement in regards to the Angstrom Exponent. The Angstrom Exponent is a unitless parameter used in atmospheric science to describe how the aerosol optical depth, a measure of how much light is blocked by particles, changes with the wavelength of light. The power law relationship, where tau lambda is the optical depth at wavelength lambda, beta represents the turbidity coefficient, and alpha is the Angstrom exponent representing the wavelength dependence. Named after Anders Knutsen Angstrom, a prominent Swedish physicist and metrologist, son of Anders Johann Angstrom, after whom the length unit, angstrom, was named. In 1929, Angstrom published a seminal paper titled On the Atmospheric Transition of Sun Radiation and on Dust in the Air. While analyzing atmospheric extinction using optical instruments, he observed that light reduction due to atmospheric dust followed a distinct power law relationship with wavelength. Initially used as a mathematical conveyance to interpolate atmospheric extinction across wavelengths from a single reference measurement, the exponent evolved as my scatter theory was integrated in the 1960s. Scientists confirmed that alpha serves as a direct proxy for average particle size. If alpha is greater than 2, the dominant fine mode particles, example, combustion byproducts, secondary organics, and fresh smoke. Small alpha, 0 or negative, is dominant coarse mode particles, wind-blown dust, sea salt, and large ash. The main usage in ground networks and satellites from 1970s to present, with growing concern over global pollution and climate forcing, the exponent became a core parameter in aerosol science. In the 1990s, NASA Aerosol Robotic Network AeroNet standardized multi-wavelength sun photometer measurements globally. Beginning in the 2000s, satellite instruments, MODIS and VIIRS, adopted derived Angstrom exponent products to establish or distinguish fine industrial pollution from coarse dust to on a global scale. Modern research also utilized the spectral curvature, second derivative of alpha across wavelength pairs, to detect bimodal particle distributions. Future directions with specialized smoke measurement. The direct link between fine combustion particles and high Angstrom exponent values derives its future application in specialized biomass burning and smoke analysis. We're going to be able to do smoke type and carbon discrimination, analyzing shifts in alpha and spectral curvature to differentiate black carbon soot from brown carbon organics, which exhibit stronger UV absorption. Smoke aging and photochemical evolution, tracking particle coagulation and secondary organic aerosols, SOAs, formation as smoke plumes transport downwind. And then sensors in situ combustion control, applying multi-wavelength optical attenuation and Angstrom principles in compact sensors to evaluate combustion efficiency and real-time smoke opacity. The first set of information we have is ethanol. Ethanol burns very clean, very low soot. Particle range was between 10 and 100 nanometers, but we can expect something between 20 and 40 nanometers. Let's see how the meters respond. We have no transmission change. We have all the light coming through, so it's not seeing anything there, but we have a minor increase in our wavelength, our color, and particle size, just a little indication, and our particle concentration is let's say it's above 0 there. Now the diodes are settling in. It looks like baseline, but it's definitely drifting down. So even the lowest burning material like alcohol with its cotton wick that's probably contributing here is detectable by the system. Our next batch of information is kerosene, a clean burning version, and particle range is 20 to 300 nanometers with a peak diameter count between 100 and 150 nanometers estimated. This is a very clean burning fuel, but we can see this. We've got definite transmission deflection, so it dropped 0.5% or so, and we've got a reduction in our mean light reaching the sensor. We've got a big change in our wavelength, and we're tracking particle size range in the 73 range right at the end of the chart there. And we have a concentration that is hitting, let's say 20 units per cubic meter. And then we have the diodes also deflecting, each in different amounts. So this is all good information for a very clean burning fuel. It is putting out a lot of measurable material, primarily incense, which has a peak count diameter of between 90 and 150 nanometers. Now, these are very small particles. A recent study done by the University of Berkeley was not able to detect particles below 300 nanometers. So we're showing that we can detect these particles and measure them or estimate the quantity and particle size within a certain confidence range. We're still tuning the system in. However, these are initial results on a proof of concept prototype. We definitely see a decline in our transmission, so a little bit of opacity in the upper left chart. We see a rise in our wavelength. We see a rise in our particle size range up to 177, and we see a rise and a decline in our concentration. We also see the diodes deflecting at different rates. So this is all very good information. It is a very sensitive instrument. It can measure very fine particles. It can measure particle diameter and particle concentration, as well as opacity. So this is a leading piece of equipment in smoke measurement.